Yes, sir.
You're running across the term somewhere in one of these of rest energy, right?
Yeah, the first one.
The first one, okay, it says rest energy. Now, I didn't use that term. The term I used was the energy due to the mass of the material, right? The mass of the particle, which is mc squared. Okay, so here's the deal. Here's how this works. When you get into more of Einstein stuff, what they'll call this is they'll call this rest energy. It's the energy of a particle sitting at rest.
Like sustain.
Yeah, just sitting there, right? But if it's moving, it's going to have kinetic energy plus its rest energy. Okay? So it's going to have 1/2 mv squared plus mc squared. And in most cases, unless it's moving really fast, this part of the energy is quite small in comparison, right? Okay. So, I think in the first one it tells you to ignore this. Is that right?
Yeah.
Okay. Ignore the kinetic energy and consider only the rest energy. The rest energy is the mc squared particle. It's the energy the particle would have if it's just sitting there.
If we're just sitting here and our rest energy is like a certain number, and when we start running,
It gets greater.
the rest energy does?
No.
Total energy gets
Your
greater.
total energy gets
Does
greater.
the rest energy go down because the energy?
Yeah. Now, when you get into Einstein stuff, they talk about there's a couple ways to view your mass and energy, because when you move faster, a lot of books, what they'll say is your energy goes into making you more massive, and you become more massive. Now, Einstein never really actually said that. What he said is your momentum increases, your MV. But people have implied that that means that your mass goes up. So most of the time people say as you move faster, your mass increases. So, but that's not your rest energy. That's your moving energy, right? Okay.
So the scales, so by that theory, that goes past your mass goes up.
Yes.
Those scales that measure trucks as they drive by are inaccurate.
Those scales that measure trucks as they go by, yes, technically, but no, practically. Because the truck's not moving fast enough to even for that be significant. Now, once you get to around the 10th the speed of light, roughly, you're going to start seeing some differences. Okay? But none of that stuff's on our exam. It's really cool to talk about, but it's not on our exam. I mean, it used to be on our exam, but not anymore. All right, we're using this time to put all the pieces together in modern, because modern can be kind of weird and different. It's not that it's that hard, it's just different, and there's a lot of little pieces, right? And what we're doing in modern is we're not really connecting all of it together, because we quickly get into math that we can't take care of. We can't get very far into quantum because we have to learn what's called wave functions and all that stuff, and so that becomes challenging. So what we're doing is we're picking out some of the highlights, some of the parts, and hopefully we can show how it all goes together. So let's look at this problem. It says, it's possible for an electron and a positron to orbit around their stationary center of mass until they annihilate each other, creating two photons of equal energy, moving in opposite directions. Okay, so you got an electron, you got a positron, okay, and they're orbiting each other. They're orbiting their center of mass. Now we don't talk about that in this class, but in Physics C, this would be relatively common. We talk about this in orbital mechanics. This would be like a binary star system, two stars orbiting each other, okay, and they're orbiting a spot in space that is the center of mass of the system, okay. If you take a barbell and you twirl it up in the air, the mass on one end, the mass on the other end, and they orbit around the center spot, the center of mass, right? If one side's bigger than the other, then the heavier one goes more towards the middle and the smaller one moves farther out. Okay? All right. A positron is a particle that has the same mass as an electron, equal but opposite charge. The amount of kinetic energy of the electron-positron pair before annihilation is negligible compared to the energy of the photons created. Okay? So they're telling you that the kinetic energy going on here as they move around is small. Okay, so we're going to ignore it. Okay, and we've talked about that a little bit already. Okay, first, calculate the EV in EVs, the rest energy of a positron. Okay, so the energy of a positron, A. All right, if we're neglecting the kinetic energy, all right, it says to neglect it, then what's the energy that the positron should have?
The rest energy?
It's just the rest energy, or the energy due to its mass itself. Okay, so we just need the mass of our positron. Or I should put that looks like a proton. P positive. Okay? A positron. All right, so all I need to do is, what's the mass of my positron? 911 e to the negative 31st kilograms times c squared
Did you say milligrams?
kilograms. I hope. All right, and there's our answer. But wait, that gives me my answer in joules, okay? So I'm going to get 8.2 e to the negative 14th joules, and then I convert that, because there is multiply or divide? Yeah. I divide by 1.6 e to the negative 19 EVs per joule, and I end up with EVs of 5.12 e to the 5th EVs. By the way, this is a relatively common answer. You'll see this a lot in modern physics. It's 0.51, usually it's 0.511 or 0.512 in this case, it rounds up. MeVs. Okay? 0.51 MeVs.
Or do an intro now?
Intro to? No.
Yeah, we did. You put the N in there.
Oh, is that what they do?
He doesn't like E's.
Oh, well, yeah. When you get into modern physics, you see this a lot, MeVs. Turns out to be a convenient unit. All right, determine in EVs the energy each emitted photon must have. Okay, look. If these spiral in, okay, and then they annihilate, okay? When they annihilate, their mass disappears, right? And all of that energy that you had from these turn into photons. Now it says it creates 2 photons, right? So one photon will go this way and one photon will go this way. Now the question is this is the energy of the positron, so what would the energy of my electron be? The same. So what will the energy of these be? The same as that, right? Because it's going to split. Why does it have to split evenly? Conservation of momentum. Because these things, as they orbit each other, what's the net momentum of the system? 0. Therefore, the net momentum after the collision must also be 0. So therefore, I've got to take away the same momentum. What's my momentum here? Momentum for a photon?
H over lambda.
It's h over lambda. They didn't ask for this, or maybe they do. I don't remember. Okay.
No, sir.
These momentums must be equal and opposite. Therefore, they must have the same exact momentum.
Same energy.
Therefore, they're going to have the same energy, right? Because E equals mc squared equals, well, hang on. E equals hf equals pc, right? So therefore, if they have the same energy, therefore, since this is a constant, they must have the same momentum, vice versa, right? So therefore, that means this photon, I'm going a long way around,
What's C?
just to say what most of you already said to begin with. E equals, what are we looking for?
The energy of one of the.
Oh, energy of the photon, which we said has to be 0.512 MeVs. All right, there you go.
So it's the same answer.
So it's the same exact answer.
How would we like an answer? Just like say conservation of momentum, therefore negative.
Yes. Now, if it says, okay, this is a really good question. The question is, how do we write that out? Now, look at what it says. In part A, it says calculate. Calculate means show the equation, show what you plug in the equation, show your work, and then show the answer. Part B says determine. When it says determine, you can just drop the answer right in. Okay, no justification required. All right? Now, usually it helps you if you write a justification down. All right, because sometimes it's worth more than 1 point. And if it's worth more than 1 point, usually if you write a little bit of something down, you'll get a little extra, right? You'll get that last point. So it never hurts to explain why. Yes?
Do you have to write the equation down too?
You do not have to write the equation. When it says determine, no algebra, no equations are required.
Is it like when they ask you a question, what happened? Do you have to explain why?
Yes.
No matter if they ask why.
Say that again?
Like, in chem, if they ask you a question, they don't.
Oh.
Why, explain it.
Well, in physics, usually, if they want you to explain with more than just a little trivial something, see, like right here, I would have said, oh, the energy of the positron equals the energy of the photon. Done. Something simple like that, or you can do it in words if you like. But usually if they want something more than just a little quickie thing like that, is they'll say justify your answer, or explain. Okay? Now, like it says in the very last question of the last one on the page, where it says explain why. Then they'd want something a little more elaborate. But even then, you should, in physics, be able to explain your answer in 3 sentences, usually. Okay, if it's more than 3 sentences, you're writing too much, probably. All right, part C, calculate the wavelength of the created photon. Okay, you got to be able to do this, right? How do I go from this to wavelength? Okay. HF, which equals HC over lambda, and then we just plug in the appropriate constant. Okay, which constant would we plug in here? The one with the EVs in it. Now watch out, if I wrote mine like this, I got to convert this to 0.512 e to the negative, e to the 6th EVs. Most of you will have 5.12 e to the 5th EVs equals, and I think your constant is what, 1240?
Yeah.
1240 EV nanometers, is that right? Over lambda. And so you'd be able to find out the lambda. Okay?
1240 over 5.2 to the 5?
Yeah, 1240, watch out though, it's in EV nanometers.
So you get wavelength in nanometers.
So what do you get?
2.42
2.42 e to the negative 12 meters. Yeah, I got 2.42 e to the negative 3rd, but mine's in nanometers. So is that right? 9, 10, 11, 12. Yes, that's the same.
9 plus 3.
I'm just making sure I get it right. I didn't use my fingers this time to count, so I'm in good shape.
I remember when I was a kid, one time I tried to count to like 13, and I was like, what do I do?
Part D, calculate the magnitude of the momentum of each photon. Okay, once again, this one shouldn't be too bad because energy equals HF equals PC. You could find it that way. That'll work. Okay? So you take your energy, plug it in here, and then divide by the speed of light, and you've got the momentum. Okay? That shouldn't be too hard. And then E, determine the total momentum of the 2-photon system. Now it says determine. A lot of times when it says determine, it's something that you might be able to do in your head. But it would help to write a little something down here because your grade will improve. So the total momentum of the 2-photon system has to be 0. Why 0? Because the original momentum was 0, so the final momentum must be 0. Okay?
Wait, but isn't momentum equal to energy?
Now wait. Momentum is a vector. We had a good question. Isn't momentum related to energy? Absolutely. Okay? So why isn't the energy 0, but the momentum is?
A vector.
Yeah, because energy is a scalar and it adds up. Momentum is a vector concept, so it can cancel out. And that's a really good question because that's confusing. Okay? In mind. Hey, everybody.
Yeah, which is throwing me off.
The question in part D is, the question was, well, why can't we just use this equation, so P equals H over lambda? And the answer is, you certainly can. This will give you the momentum. That's just the way I did it. But when I'm working at the board here, I thought, well, I can work it this way, right? And I'll get the same answer.
Just different units.
Maybe.
Is that what's this? Because you got like 2 minutes.
Yeah, what's the
Yes.
units for the PCO?
What's the units for PC? Okay, well, this is momentum. This is speed of light. So if you work it this way, this is going to be units of, momentum is kilogram meter per second, and that is meters per second. So you get kilogram meters squared per second squared, which is a joule. So that would have to be in joules. If you're going to work it that way.
And what's the units for momentum?
Momentum, standard units for momentum are kilogram meter per second.
But you can also use EV seconds per meter.
Or if you work it this way, you could end up with EV seconds per meter. But you got to put those units down properly. You're going to get credit.
That's why
All right, let's confirm this because we have lots of questions on this. And the units in this section, you'll notice that in physics, usually the units are really straightforward, which is the great thing about physics, is we keep a standard set of units.
And we hit chemistry.
Well, chemistry is just a little more challenging because chemistry has lots of different units, and you have to really be careful which units you got.
And there's
Okay,
a lot
now that we're in modern physics has come up with different sets of units to work with the atomic scale because it makes it more convenient. We're picking a play out of the chemistry handbook there, and we're using units the way chemistry does, which is pick whatever is convenient and use that unit, okay? Which is fine. So E equals HF equals PC. So P equals E over C. All right, now look. Look, if I put this energy in, I get 5.12 e to the 5th EVs divided by 3E8 meters per second. Okay, if I solve this, my units, be very careful. Carry your units around with you when you're working modern physics problems because it's not very intuitive what your units are. It's not like when you're in mechanics and you know mass is always kilograms and velocity is always meters per second. Okay, over here it's not that way. So please be careful. My units are coming out as EV over meters per second, which is EV seconds per meter. That is an okay unit on the exam, only if you put it on your answer. Okay? If you don't put units on your answer, they're not going to give you credit for some crazy number here. Yes?
And you have to carry that same unit onto a problem if it needs that part?
Yes. That's exactly right. So since I found this earlier, I got to carry that unit with me unless I want to convert it. Okay? So somebody help me out here. What does this become?
Electron volt second per meter.
No. What's the number?
Oh, so momentum is 0.0017.
0.0017. Okay, now, lots of you were saying, well, why can't I work it this way? That lambda equals h over momentum. So momentum equals h over lambda. So let's work it that way. What's my wavelength? Well, it was 2.42 e to the negative 12 meters. Okay, now, which h do I use? You would probably use the one with joules, because then that would make your momentum come out in standard units, right? Which is 6.63 e to the negative 34th, is that right?
Yeah.
Joule seconds? Okay, if I work that out, what do I get?
Same answer.
No.
No?
Well, yes and no.
2.7, yeah, 2.74 e to the
Yeah.
2.74 e to the what? Negative 22nd? kilogram meters per second. Okay, now look, I got this answer and I got this answer. Which one's correct? The answer is yes, they are both correct.
Joule seconds over meters. Like you did
Joule, if you want to leave this as joules seconds per meters, that's okay. That's an acceptable unit because it is correct. Yeah, if you don't remember what a momentum is, because a momentum doesn't have its own separate unit, so that'd be okay as long as you carry it correctly through.
But you know what I mean. You don't.
All right. Prove to me these are the same. Prove these are the same. How would I do it?
multiply by 1.6, whatever.
Yeah, 1.6 e to the negative 19 joules per EV. And if I do that,
Is that 0.00?
EVs will cancel out.
EVs will cancel and I'll get joule seconds per meter, which is a kilogram meter per second. And I hope, are they close? Are they off by just a little? Yeah, it's probably a rounding issue, right? Okay, those two should be the same, or within a rounding. All right, so there you go. So you need to be careful when you're working these problems. Okay, now, work the one on the bottom of the page. There's a full other problem. Hey, this is another great question. The question is, well, we know the mass of an electron, so why can't we plug the mass of an electron in? It's because it makes it so much simpler, number one, is if you just leave it with the symbols. Plus it says, express all algebraic answers in terms of the given quantities, and the mass of the electron is given as m. And fundamental constants. So it's all going to be symbols. Except for a few random numbers like 1/2 in the kinetic energy equation. All right, first thing, we have an electron that has a mass m. Moving to the right, they ask for what's the kinetic energy of the electron. Hey, K equals 1/2 mv squared. Done. Like this problem so far. Part B, what's the de Broglie or de Broglie wavelength of the electron? Well, that would be wavelength equals h over its momentum. Planck's constant over momentum? H over mv. Done. What's that? What'd you get? Okay, now we've had several people ask that question. The question was, why can't I put MC here? And here's the reason. You notice above, in the question above, part, I don't remember which part it was, part D or whatever, I put MC in for momentum. But here's the critical difference. This is an electron with a velocity. The one I did before was a photon, and a photon moves at the speed of light. And so since it's an electron, I have to put its physical velocity in. I can't use the speed of light because it's not traveling at the speed of light. Okay? All right, part C. So far, I'm really loving this problem. Part C. An electron encounters a particle with the same mass and opposite charge, a positron, moving with the same speed in the opposite direction. So I have my electron, I have my positron, moving at each other, same mass, same velocity. Ooh, dead giveaway already. Hey.
I thought I had changed.
Oh, thank you. Dead giveaway. Same mass, opposite direction, collide. Momentum of my system is 0, right? Okay, we're going to need that later. Determine the energy of each photon. I'm sorry. Oh, yeah. Hang on. Part C. Shh. I forgot the question. The two particles undergo head-on collision and result in the disappearance of the both particles, and they produce two photons of the same energy. Then they say, what is the energy of each photon? All right. So what we have to do is figure out what energy did I start with. Well, the energy is the rest energy plus the kinetic energy. Now, some of you said, look, there's energy for this one and energy for this one, all right? But we know it's going to split up into two photons, so the energy of one will go into one photon, the energy of the other will go to the other photon, right? Okay. Some of you said, can I just put down this? Because up above it says, v is much, much less than the speed of light? And the answer is yes, you can. They accepted two answers. The two answers are mc squared or mc squared plus 1 half mv squared. Either one is acceptable. So they're both correct. And then it says, part D, what's the wavelength of each photon? This seems like a repeat, doesn't it? Wavelength equals,
Well, energy is
Just like the
okay? Energy is equal to what?
HC over wavelength. So energy is HC over energy, and
Okay.
energy is MC squared. MC is MC, so wavelength equals H over MC.
You're going way too fast for me.
Wavelength equals HC over E, and
All right.
E was equal to MC squared.
Oh, yeah, that works.
And then C's cancel. Goes to H over MC.
Okay? Hey,
Hold on.
and look at that. That's the same thing as,
Bye.
but for a photon,
C is it. It's D.
look at that.
Oh.
Now, for those of you that did not neglect this part, then the way you would do this is you would say it's HC over MC squared plus 1 half MV squared. And you just carry it through like that. You just leave it. And that's perfectly acceptable. Okay? So this answer is correct, as is this answer.
Well, to match, like for C and D, if you put the whole thing, would you
Yes,
take the whole thing?
good question. If you put only this here, then this has to be your answer for this one. If you put the whole thing in, then this has to be your answer, because they have to be consistent. That's correct. All right, very nice. And then it says E, explain why two photons are produced instead of one. That has to do with conservation of momentum. We started off with no momentum. There's no way to get a single photon and no momentum,
Because they have no.
because they all have momentum. So therefore, you have to produce at least two in the opposite direction. If you produce two, they'll be equal and opposite. If you produce three, that's possible. Then you could have two go this way and one go this way. There's all kinds of possibilities, right? But you have to have at least two.
108.
Everybody, shh, listen up. Okay, the question was, do we have to know what the elements are? And the answer is no. This is a physics exam, not a chemistry exam.
Okay, well,
So you would have to be able to calculate the A number and the Z number, atomic number and atomic mass number, right? And you'd have to be able to calculate the energies and the masses and, you know, the equations. But whether you have to figure out what that element is, no. You don't have to know what the name of it is.
because unit.
Okay, gotcha. Okay, U in physics equals AMU in chemistry. All right, now, when in doubt and you can't figure out what that is, what do? No, you look it up on your constant sheet. 1U equals 1.66 e to the negative 27 kilograms, I believe.
Or
Okay.
31 mega E.
Yeah.
Oh yeah, or they have it in MEVs as well. Okay, first thing, it says you have unstable nucleus, it's initially at rest, decays into a nucleus of fermium containing 100 protons and 152 neutrons and an alpha particle. Okay? The atomic mass of helium and fermium are given respectively, and they're given in units of atomic mass units. What's the atomic number of the original unstable atom? Okay, so we're starting off, remember, we're starting off with something that has two numbers, A number and a Z number. It's turning into fermium, which I believe is Fm, and the fermium is 252 and 100 and an alpha particle, which is 42. So they want to know the atomic number.
102.
Okay, that's this one. So that's a 102. They're checking to see if you know which one's which. This is the atomic mass number up here, which would be 256, right? And we still don't know what that is off the top of our head. We have to look that up. Okay, element 102. All right, so our answer is 102. Okay, what's the velocity of the alpha particle?
Kinetic energy is 8.42.
Okay, here's the deal. Where does the velocity of this come from? Where do we get this kinetic energy?
From the mass defect.
From the mass defect. So, what's our mass that we lose? Oh, it gives us the kinetic energy.
Yeah.
All right, so that's their kinetic energy.
So you solve for mass defect?
Well, hang on. So that energy that you get, we might have to solve for mass defect. I don't know. That's a great question. I was thinking you had to solve for it. I didn't realize that they gave you the energy. Listen. If they had asked for this kinetic energy and not already given it to us, the only way for us to find it would have been to find the mass here and the mass here, do the mass defect, and then E equals mc squared and find it. But they gave it to us, so we're in good shape. 8.42 MeVs, that's the energy, and they're saying that's kinetic energy, which is 1/2 mv squared. Okay?
They gave us the mass.
And they gave us the mass of our alpha particle. So I've got 8.42 MeVs equals 1/2 m, which is 4.00260, but that's an atomic mass unit, so I need to convert that and get v squared eventually. So my conversion is 1.66 e to the negative 27. That's kilograms per atomic mass unit. Now I still got issues
Yeah.
because I'm now in kilograms over here, and I'm going to get a crazy unit for velocity. So I need to convert MeVs into something.
Why can't you just throw it all over there?
To a joule.
You could if you want, but you better make sure your units are right. So if I want to convert this to joules, first of all, this is e to the 6th, and then I got to multiply this side by 1.6 e to the negative 19 joules per EV.
What if I convert wrong? That's not my answer, though.
A lot of the newer tests, because there are multiple ways you can answer it, depending on what units you put, they put down what's the velocity in meters per second. So you have to convert it.
There.
So watch out. Okay, what do you get? You get a better number now?
2.1. 2.01.
2.01
7.
e to the 7th meters per second. Okay? Now that's fast. Is it too fast?
No.
Okay, we're okay. We're less than the speed of light, so it's at least reasonable. Okay, now it says, where does the kinetic energy of the alpha particle come from? We just explained that. It's from the mass defect. Mass defect converted into kinetic energy. Now they could have asked you what the mass defect is, in which case you would have taken this energy and you would E equals mc squared it to figure out what the mass defect is. So they could have asked you what the original mass of this thing is, if they wanted to. It wouldn't have been that hard. You take this energy, convert it into mass, convert it into atomic mass units, and then add it to these two, and that would be the original mass of what they generally call the mother particle, and these are the daughters. Okay?
Father.
Yeah, I don't know. That's the terminology you'll hear sometimes. It's the mother and the daughters. Okay? And then you might just want to put, just for grins, E equals mc squared, just to show your intelligence. Guarantee a good grade. Okay, it says, suppose the fermium could undergo a decay with a beta particle. How would this affect the atomic number of the nuclei, or nucleus? Okay.
It would be 103.
Okay? Okay, a beta particle, what's its numbers?
Zero.
Negative 1, right? So that means whatever we get here, you're going to end up with a 252, 103. So the answer is, the atomic number would go up by 1, because the beta particle is a negative 1 particle.
Fermium is 100, not 102.
Yeah,
What?
You have it reversed.
Oh!
Switch your fermium and your unknown.
So I wrote down the wrong thing here.
But he has it.
So this is 100. That's 101. There you go. Sorry, I wrote the wrong number down. I think I have it wrong in my key as well.
No, it was fine.
Was
Oh
it?
wait, no, it was wrong.
I think my answer is still correct, but my explanation was wrong.
No, the explanation was right as well.
Is it right?
I think
Okay.
it was.
All right, so the answer is it goes up by 1. Okay, there's a nuclear reaction. Let's do we need to do a photon one. I think we've already done a couple of photoelectric ones. We need
What
to do
about
a
the cat?
photon energy level one.
Oh, yeah.
37 says, the energy level diagram for atoms that comprise a helium-neon laser are given above. As indicated on the left, the helium atom is excited by the electrical discharge and an electron jumps to the energy level E0. You move from energy level 0 to energy level 2. The helium atom, atomic mass 4, then collides inelastically with the neon atom, atomic mass 20, and the helium atom falls to the ground state, giving the neon atom enough energy to raise the electron from energy, right here, E0, to energy E2. All right, so it goes from here to here. Right? Inelastic collision makes it go up there. All right, there's a lot of words. The laser emits light when the electron in the neon atom falls from energy E2 prime to energy E1 prime. Okay, whoa.
So I fell from the electron.
Now it says, calculate the minimum speed of the helium atom that must have in order to raise the electron from here to here. Look, what's it saying? It's saying that helium is colliding with this and making this happen. Okay, look. How much minimum energy must the helium have to make this occur? 20.66 EVs. All right, so the energy that's required is 20.66 EVs. So that will be the kinetic energy, right? Which equals 1/2 mv squared. Very good.
Don't try to cover it up with.
Did everybody catch that?
Yeah.
No.
So the kinetic energy of the helium is what causes us to jump from here to
They
here.
gave us mass.
Since they gave us the mass of this, which is right, atomic mass 4, okay? So this would be 1/2 4U, but I'm going to have to convert that, 1.66 e to the negative 27 kilogram per U. V squared equals 20.66 EVs, but oh, now I got EVs. So I got to convert that, 1.6 e to the negative 19 joules per EV. Okay, now, shh, I need your attention. This is not that hard. It's a lot of words, so it's hard to follow, okay? But in order to get this electron from here to here, it requires that much energy, so that must have that much kinetic energy, so you'd have to convert all your units, right?
What's the mass? 1.6 to the negative 19?
The mass of the helium is 4, but that's in atomic mass units, so you got to convert that to kilograms, and you got to convert your EVs to joules, so all the units work out.
I like how I kept it simple instead of all on the top. They're like 4.5.
I know. In this one, they realized that this was already a confusing problem, so they just gave you 4, which was nice. You end up with velocity of 31,550 meters per second. All right? Okay, we're almost out of time. Listen before you go. Listen before you go. Make sure you understand photoelectric effect, because that could be on there as a free response. Make sure you understand Compton effect, because that could be on there as a free response. Make sure you understand these types of problems. So make sure you work these, because this is the one we didn't really work in class. The electron jumps, because that could be on the free response. And then a nuclear could be on the free response. And then kind of like one of those last ones, just a kind of a mishmash of things, right? There's a lot of stuff, but you can do it.